What existed before the Big Bang? This is one of the most important questions in modern science. Many of us were taught in school that the universe began with a massive explosion called the Big Bang. We learned that everything, space, time, matter, and energy, started from a single point and began expanding. But here's something important. The Big Bang was not an explosion in empty space. It was the expansion of space itself. And according to current scientific understanding, time also began at that moment. So when we ask, what happened before the Big Bang? We may be asking a question that doesn't fully make sense, because if time began there, the concept of before may not apply. In this video, we're going to clearly explain what the Big Bang theory actually says, which scientists developed it, what evidence supports it, and what science still doesn't know. Let's start from the beginning. To really understand the Big Bang theory, we need to look more closely at the work of the scientists behind it. In 1927, Georges Lemaitre carefully studied Einstein's equations of general relativity. Instead of assuming the universe was static, he allowed the math to speak for itself. The equations showed that space itself could either expand or contract. Lemaitre proposed that the universe is expanding, and that if we reverse that expansion backward in time, everything would shrink into an extremely small, dense state. He called this the primeval atom hypothesis, the early version of what we now call the Big Bang theory. Then came Edwin Hubble. In 1929, using powerful telescopes, Hubble observed distant galaxies and measured their light. He discovered something remarkable. The light from most galaxies was shifted toward the red end of the spectrum. This red shift meant the galaxies were moving away from us. Even more importantly, the farther a galaxy was, the faster it was moving away. This became known as Hubble's law. It was direct observational evidence that the universe is expanding. Now let's talk about Albert Einstein. In 1915, Einstein developed general relativity, a theory explaining how gravity works as the curvature of space and time. When he first applied his equations to the universe, they predicted expansion or contraction. But Einstein believed the universe was static, so he added a cosmological constant to force the equations to stay balanced. Later, after Hubble's discovery, Einstein reportedly called this his biggest mistake because the original equations already supported an expanding universe. Finally, in 1965, Arno Penzias and Robert Wilson made a discovery that strongly confirmed the Big Bang theory. They were working with a radio antenna and kept detecting a faint uniform microwave noise coming from every direction in space. At first, they thought it was interference, even checking for bird droppings in the antenna, but the signal would not disappear. Scientists later realized this radiation was the leftover heat from the early universe. It became known as the cosmic microwave background, essentially the afterglow of the Big Bang. So mathematically, observationally, and experimentally, the theory was supported step by step, first through equations, then through telescope observations, and finally through measurable radiation that still exists today. If we go back to the very beginning, as far back as our physics allows, the universe started in an extremely hot, dense state. This is often described as a singularity, but we need to be careful with that word. A singularity simply means that our current equations break down. It does not necessarily mean there was literally an infinite point. It means our physics cannot fully describe that moment yet. At time zero, or more accurately at about 10 to 43 seconds after the beginning, which is called the Planck time, the universe was unimaginably hot. The temperature was so high that the four fundamental forces of nature may have been unified into one single force. These forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today they act separately, but at extremely high energy levels they may behave as one. We do not yet have a complete theory that combines gravity with quantum mechanics. This is why the very first fraction of a second is still not fully understood. Scientists are still searching for a theory of quantum gravity to explain it. Immediately after this earliest phase, something extraordinary happened: cosmic inflation. During inflation, the universe expanded incredibly fast, faster than the speed of light expansion of space, which does not violate relativity because space itself was expanding. In a tiny fraction of a second, The universe grew from subatomic size to something macroscopic. This rapid expansion explains several mysteries. It explains why the universe looks almost the same in every direction. It explains why space appears geometrically flat on large scales. And it explains why tiny quantum fluctuations in the early universe later became the seeds of galaxies. After inflation ended, the universe was still extremely hot, filled with a dense mixture of energy and elementary particles. Quarks, electrons, neutrinos, and photons were constantly interacting. Because the temperature was so high, particles and radiation were in constant equilibrium, colliding and transforming into one another. As the universe expanded, it cooled. Within the first microseconds, quarks combined to form protons and neutrons. This process is called hadron formation. Then, within the first 3 minutes, something very important happened: Big Bang nucleosynthesis. Protons and neutrons fused together to form the nuclei of light elements, mainly hydrogen, helium, and small amounts of lithium. At this stage, about 75% of the universe was hydrogen, and about 25% was helium by mass. These proportions still match what we observe today, which is strong evidence supporting the theory. However, even though atomic calculate mathematically. After the universe became transparent at around 380,000 years, it was filled mostly with hydrogen and helium gas, with tiny density fluctuations left over from the quantum fluctuations during inflation. These tiny variations in density were critical. They were the seeds that would grow into stars and galaxies. Gravity began to act on these small irregularities. Regions with slightly higher density pulled in more gas from their surroundings. Over millions of years, these regions grew larger and denser. Eventually, pockets of gas became dense enough that nuclear fusion could start in their cores. The first stars were born. These first stars were very different from most stars we see today. Scientists call them population 3 stars. They were massive, sometimes hundreds of times the mass of the Sun, and extremely hot. Because the universe at this time contained mostly hydrogen and helium, these stars lacked heavier elements. That made them burn hotter and live shorter lives, just a few million years compared to billions of years for smaller stars like our Sun. When these massive stars reached the end of their life cycles, they exploded as supernovae. These explosions were critical because they produced the first heavy elements: carbon, oxygen, iron, and others. Without these heavy elements, planets like Earth and even life itself could not exist. Over hundreds of millions of years, gravity continued to pull matter together. Groups of stars formed clusters, and clusters formed galaxies. Our galaxy, the Milky Way, is one of countless galaxies in the observable universe. It contains billions of stars, many of which host planets. About 4.6 billion years ago, within a cloud of gas and dust in the Milky Way, our solar system began to form. Gravity caused the cloud to collapse into a spinning disk. The Sun formed at the center, and leftover dust and gas gradually coalesced to form planets, moons, asteroids, and comets. Earth was one of these planets, born from the remains of ancient stars. Essentially, every atom in our bodies, every element on Earth, came from stars that lived and died billions of years ago. This process, from the Big Bang through nucleosynthesis to star formation and planetary systems, shows how interconnected everything in the universe is. What began as a nearly uniform hot plasma eventually became the structured, complex cosmos we see today. After understanding how the universe evolved into stars and galaxies, the next big question is, what was before the Big Bang? First, we need to understand something fundamental. Time itself began with the Big Bang. According to general relativity, time and space are part of the same fabric. space-time. If space-time started at the Big Bang, then asking what happened before may not even make sense in a conventional way. There may not have been a before as we understand it, but physicists still try to explore possibilities. One of the most important ideas is cosmic inflation, proposed by Alan Guth in the 1980s. Inflation suggests that immediately after the Big Bang, the universe expanded exponentially in an extremely short fraction of a second. The scale of the universe grew by a factor of at least 10^26 in less than a trillionth of a second. This explains why the universe appears so uniform and isotropic, almost the same in every direction, and why space is geometrically flat on large scales. Inflation also left behind tiny quantum fluctuations, small variations in density and energy. These fluctuations, though microscopic at first, became the seeds for galaxies and galaxy clusters billions of years later. Essentially, the large-scale structure of the universe came directly from quantum events at subatomic scales. Another idea scientists explore is the multiverse theory. In this scenario, our universe is just one bubble among potentially infinite other universes. Each universe could have different physical laws or constants. Some multiverse models even suggest that universes continuously bud off from inflating space. While it's speculative, it provides a framework to think about why our universe has the properties it does. There is also the cyclic universe model, which proposes that the universe goes through endless cycles of expansion and contraction. In this scenario, the Big Bang might not be the absolute beginning. It could be just the latest phase of an eternal cycle. Gravity eventually pulls everything back, leading to a big crunch, and then a new expansion begins, possibly repeating infinitely. Finally, quantum physics gives us another perspective. Even a vacuum in quantum mechanics is not truly empty. Virtual particles constantly appear and disappear. Some physicists hypothesize that the universe itself could have arisen from a quantum fluctuation in a vacuum. In this sense, the origin of the universe may not require a cause in the classical sense. It could be a natural consequence of quantum rules. All of these ideas, inflation, multiverse, cyclic models, quantum fluctuations, show that science is still trying to understand the very beginning. The Big Bang theory explains everything after a tiny fraction of a second, but the first instance, and what may lie beyond, remain deeply mysterious. The key takeaway is, the Big Bang is not just an explosion. It's the birth of space, time, matter, and energy. And even today, billions of years later, we are still connected to that origin. In the atoms that make up our bodies, the stars we see, and the light that travels across the universe. When we talk about the very beginning of the universe, traditional physics, like general relativity, breaks down. Time and space as we know them cannot describe the state at time zero. This is where quantum physics comes in. In quantum mechanics, even what we call empty space is never truly empty. Instead, it's a seething sea of energy called the quantum vacuum. Tiny particles appear and disappear constantly. These are called virtual particles. Normally, they pop into existence for an incredibly short time and then vanish, leaving no lasting trace. Now imagine this quantum vacuum on a cosmic scale. Some physicists hypothesize that a large quantum fluctuation in this vacuum could have created a tiny region of energy, dense enough to trigger the Big Bang. This fluctuation would not need a cause in the classical sense. It's allowed by the laws of quantum mechanics. In other words, the universe may have popped into existence naturally without any external reason. These quantum fluctuations were not just random noise, they were incredibly important. During the period of cosmic inflation, these tiny fluctuations were stretched from subatomic scales to macroscopic sizes. These stretched irregularities in density became the seeds for the structure of the universe. Later, as gravity pulled matter together, these tiny fluctuations determined where galaxies, stars, and clusters would eventually form. In short, the first tiny differences in energy caused by quantum fluctuations eventually became the cosmic patterns we see in the universe today. The ripples in the cosmic microwave background, the afterglow of the Big Bang, are direct evidence of these early quantum fluctuations. Without these quantum fluctuations, the universe would be completely uniform. There would be no galaxies, no stars, no planets, and ultimately no life. So, quantum physics doesn't just explain the small world of atoms. It may also explain how the universe itself began and structured itself. Immediately after the universe came into existence, possibly triggered by a quantum fluctuation, something extraordinary happened: cosmic inflation. Inflation is a phase where the universe expanded exponentially, growing from a subatomic size to something macroscopic in less than a trillionth of a second. This expansion was not a conventional explosion. Matter itself didn't move faster than light, rather space itself stretched. This is allowed by Einstein's theory of general relativity. Why was inflation so important? There are several key reasons. 1. Solving the horizon problem. Before inflation, different regions of the universe would have been causally disconnected, meaning light or information could not travel fast enough to make them uniform. Yet today, the universe looks almost the same in all directions. Inflation explains this because regions that were initially microscopic got stretched, making distant areas appear uniform. 2. Flattening the universe. Inflation also explains why the geometry of space is nearly flat. Without inflation, curvature could have caused a highly curved universe collapsing too quickly or expanding too fast. Inflation stretches space so dramatically that any initial curvature becomes almost invisible. 3. Amplifying quantum fluctuations. During inflation, tiny quantum fluctuations from the vacuum, the ones we discussed in part 16, were stretched to enormous scales. These fluctuations created slight variations in density, which later became the seeds for galaxies, stars, and galaxy clusters. Think of it like this. Inflation took a microscopic blueprint and blew it up to cosmic size. Every ripple and tiny imperfection in the early universe eventually led to the vast structure of galaxies and clusters we see today. Inflation lasted only a tiny fraction of a second, but its effects shaped the entire universe. Without inflation, the universe would likely be chaotic, non-uniform, and perhaps incapable of forming galaxies, stars, or life. Finally, inflation is supported by observations, especially the cosmic microwave background, CMB. Tiny temperature variations in the CMB match the predicted fluctuations from inflation. This is one of the strongest pieces of evidence we have for the theory. In short, cosmic inflation is the bridge between the quantum scale at the birth of the universe and the cosmic scale of stars and galaxies. It transformed randomness into the structured universe we observe today. Once we understand cosmic inflation, it naturally leads to the concept of the multiverse. During inflation, some regions of space may stop inflating while others continue. In this picture, our universe is just one bubble in a vast, possibly infinite foam of universes. Each bubble is like a separate universe, with its own space, time, and physical laws. Here's what makes this idea so fascinating. 1. Different physical constants. Each bubble universe could have different values for fundamental constants, like the strength of gravity, the speed of light, or the masses of particles. Some universes may be completely inhospitable to life, while others might be similar to ours. 2. Eternal inflation. Inflation might not have stopped everywhere. While our bubble universe stopped inflating, other regions could still be inflating, creating new bubble universes continuously. This leads to the concept of eternal inflation, an ongoing process of universe formation that never truly ends. 3. Implications for our universe. The multiverse idea could explain why our universe seems so finely tuned for life. Out of countless universes, we naturally exist in one where the physical constants allow galaxies, stars, and planets to form. This is sometimes called the anthropic principle. 4. Observational challenges. The multiverse is still speculative because, by definition, other universes are beyond our observable horizon. We cannot directly see them, but subtle clues may exist. For example, if another universe collided with ours in the very early cosmos, it could leave an imprint on the cosmic microwave background. 5. Philosophical implications. If the multiverse exists, it changes our perspective on reality. Our universe may not be unique. It could be one of countless others. Everything we know, and space, time, matter, might just be one bubble in an unimaginably vast cosmic landscape. In short, the multiverse idea takes inflation and quantum fluctuations to the next level. It suggests that our universe is part of a much larger, richer reality. And even if we cannot directly observe other universes, the math of inflation and the patterns in our own universe make this possibility plausible. While the standard Big Bang and inflation model explain most of what we observe, some physicists explore alternative possibilities. One of the most intriguing is the cyclic universe. The cyclic universe theory suggests that the universe does not have a single absolute beginning. Instead, it undergoes an endless sequence of expansions and contractions, a cosmic cycle. Each cycle could include one expansion phase. Similar to our current universe, space expands. Galaxies, stars, and planets form. Inflation or similar processes could occur in each cycle, stretching space and seeding the structure of the universe. To contraction phase, Big Crunch. Eventually, gravity might pull the universe back together. In this Big Crunch, all matter, energy, space, and time collapse into an extremely dense, hot state. Thrikasa bounce a new Big Bang. After the Big Crunch, a new expansion begins, essentially a new Big Bang. This creates a fresh cycle of universe formation, potentially with new physical constants or properties. Why consider a cyclic universe? Explains flatness and size. Each cycle could naturally reset the universe, explaining why space appears flat and homogeneous today. Avoids absolute beginning. In this model, there is no singular first moment. Time could be eternal, stretching infinitely into the past and future. Connects with quantum physics. Quantum mechanics suggests that extremely dense states could trigger a bounce instead of a singularity. This gives a mechanism for the universe to transition between cycles without a true beginning. Challenges and speculation. While mathematically interesting, direct observational evidence for cyclic models is limited. Some proposals predict subtle signatures in the cosmic microwave background or patterns in gravitational waves, but none have been definitively detected yet. Big picture. The cyclic universe is part of a broader effort to understand the pre-Big Bang question. Along with quantum fluctuations, inflation, and multiverse ideas, it shows that cosmologists are pushing the limits of human understanding. Even if we don't yet know the absolute origin, these theories show one thing clearly. The universe may be far richer and more complex than our textbooks suggest. And importantly, these alternative models remind us that science is never about certainty, but about building explanations that best fit observations, while always leaving room for new discoveries.